So the last topic for this section 14.2 is about integrating vector valued functions. Well, so no new rules, no new integration methods. All methods you know from since Calc 1, Calc 2. We're just going to put them in the vector valued function context. Well, but how do we put this together? Number one, well, so we'll be given a vector valued function in linear combination notation or in component form, and it may be, um, it may be a vector in the plane or a vector in space. So in this case, this lowercase f, g, and h represents the given integrand, and this uppercase f, g, and h represent the antiderivatives of those little f, g, and h. All right. And well, so the indefinite integral of a vector valued function, in the same way we integrated f of x to get, the integral of f of x dx to get big F plus c. Well, we will also get a constant of integration when it comes to getting the indefinite integral. All right, how is that going to work? Number one, in this case, this c, however, it's not just going to be one constant. Notice how this c is a bold case. So this c represents a vector. What is that vector made of? Well, so because we're integrating components f, g, and h, each component will have its own constant of integration. It may be the case that it's the same for the three of them, or the two, depending on if it's a vector in plane or space. Or we may get the three or the two different constants of integration. So that's why it has to be expressed as a vector. So the integral of r of t. So that's integrating the integral rather of f, g, h as a vector valued function. Integrate each. Integral of f, integral of g, integral of h. That's going to be big F, big G, and big H. Notice the constants of integration here. They are C1, C2, and C3 to represent or to denote the constant for each of the components. So that's one of the ways to express this. Another way to express this is a single vector with the antiderivatives or the integrals and a separate vector for the constants of integration of each individual vector. So, or rather component. Now, for a vector valued function that we integrate within limits, that is using the fundamental theorem of calculus, we will do the same upper limit minus lower limit for the x component, upper limit minus lower limit for the y component, and upper limit minus lower limit for the z component. All right. So essentially, we would be evaluating 2 or 3 integrals in the same problem. Right. That's all it's going to be. Okay, so let's have a look at this to see this in action actually. So what do we have? Evaluate the integral of this vector value function. The integral of 8t, comma 1 over 4 plus 9t squared, comma the integral, comma 3 over 5 minus t. Alright, so the final answer should be one single vector. Could be a big expression or something tiny. Well, we'll see. So what the way I usually like working this is evaluating each separate integral. That is the integral of 8t dt. That is 8t squared over 2 plus, in this case, let's call this c1 because that's the first integration we're doing. That's for the x component, and reduce 8 over 2. That is 4t squared plus c1. What about letter B? The integral of 1 over 4 plus 9 t squared dt. Alright? Any ideas about this integral? How do we evaluate it? The arctangent, right? What if we had a t right here in the numerator instead of a 1? Use substitution, but in this case we don't have that t, so arctangent rule. However, be careful with the arctangent rule. Although it's not a hard rule to deal with, but it may be a little tricky when you have numbers other than simply a 1 here or simply a 1 for the coefficient of the variable term. So my advice for integrals that yield inverse trig functions, always write them like quantity squared, that is 2 squared plus, what is this? 3t quantity squared. And then let me put the dt here, all right? This so you can identify the a and the u, because when it comes to, but I mean, we will still have to do a baby u substitution, maybe nothing too crazy, but still this little coefficient is gonna make a huge difference when it comes to setting it up. All right, so let's see. So number one, a equals to 2 and u equals to 3t. That means du equals to 3 dt, which means dt equals to 1/3 du. All right? So now let's write the integral in terms of u. So that is the integral of dt, but I'm going to replace the dt with 1/3 du and divide this by, what's that? A squared plus u squared. This is going to be 1/3 arctan of u over a. All right, do you guys agree with this? Yes?
How did you know to use the arctan?
That's because it's a sum in between the two terms. It's a sum of squares. The other rules involve, number one, they involve radicals, and you would see a differences of two squares. All right? So, but I'm missing something here, I think. What is it? 1 over a, right? So that's 1 over a right here. Don't forget that 1 over a. It's not a 9, it's an a. Make it look like an a. There you go. So that is 1/3 times 1 over a, which is 2. So that's why I wrote the integral like this. So you can see these a's, these u's. So that's 1/2 arctan of u, which is 3t, over a, which is 2. Oh, that's already plus c2 plus c2. That equals 1 over 6 arctan of 3t over 2 plus c2. All right? So that's our second integral. Let's go about the third integral. Okay, letter C. I'm going to go about letter C. So, for letter C, let me set up the integral first, and that's the integral of 3 over 5 minus t dt. Any ideas how to solve how to evaluate this integral? It's going to be the ln rule. I use up with an ln rule. Okay. I mean, here's the thing. If you want to set 5 minus t equals to u, then you do the du, which is going to be -1, and then you will have to do the minus du. That's fine. However, here's the little trick I'm going to do. I will take out number one. Number one, I will take out the 3 outside of the integral. I'm going to call this dt over, instead of 5 minus t, I'm going to write it as t minus 5. That is reversing the order of the terms. But in order to achieve this, I would need to multiply everything by negative. And with this, you may bypass the showing the u du substitution. However, you can do it the other way if you feel more comfortable with it. Okay? So that'll be -3 ln of the absolute value of t minus 5. Don't forget the absolute value bars here. Don't forget also the C3. So we have the answer to the integral of this vector valued function. All right, that is a whole new vector where the first component is 4t squared plus c1, comma, 1/6 arctan of 3t over 2, plus 2, plus c2 rather, and -3 ln of absolute value of t minus 5 plus c3. Okay? So that's our final answer. Yes, we're going to get these big vectors here as final answer, because, you know, some of these results get really big. Okay, there you go. All right. What about another kind of integral? It's the same integration method. It's now that we have limits of integration. Again, this is what we're going to do. I'm going to set two integrals separately, but in this case, these are going to be definite integrals. Our final answer, yes, it's going to be a vector. However, it's not going to be a variable vector, a vector that involves these huge expressions like what we did in the previous example. It's going to be numerical components because, again, the definite integral is going to output a constant value, all right? So, and again, I'm going to set these two separately. That is the integral from 0 to pi over 2 of 3 sine squared t cosine t dt, and then I'm going to set a separate integral for the second component. All right. Any ideas how do we evaluate this integral? Another u substitution, right? That is, what would our u be in this case? Sine, right? Typically our u is whatever is inside parentheses. Well, I don't have parentheses here, but I can, in a way, write these parentheses, make this a square if you want. That's fine. Everything inside a radical, everything in the exponent of an exponential function. That's typically our choice of u. In the most straightforward cases. There are other cases in which we may need to manipulate those expressions before getting a u, but well, that's something else. So, u equals to sine t, du equals to cosine t dt, right? Well, actually, this is going to be very straightforward. Now, here is the thing. And here is where you may do this however you want. What I'm going to do is what I prefer because it saves me time when it comes to evaluating definite integrals. A very typical approach for definite integrals is just to integrate the usual way, ignore the limits of integration, and then just put them back in once you're done with the integration. However, the correct way technically to evaluate an integral, because this is what we're doing. Every time we're doing a u substitution, we are trying to solve a complicated problem in the world of t or in the world of x. So we're sending it to the world of u to simplify the problem, solve it in the world of u, and then once you're done solving in the world of u, go back to the world of x, or well, in this case t. That x was back in calc, right? Calc 1 or 2. So what we're trying to say here is, if we are setting a u for the expressions technically, we need to express the limits in the corresponding world of u. That is, evaluate u at the lower limit, evaluate u at upper limit. That is, sine 0, which is 0, sine of pi over 2, that equals 1. All right? So now what do we have? The integral between 0 and 1, let me take out the 3, that is u squared du. That is 3u cubed over 3, evaluated between 0 and 1, and that's about it, right? So that is u cubed, that reduces to u cubed from 0 to 1. What is this? 1 cubed minus 0 cubed. That equals to 1. And that's the first component of the vector. Do you see how we are saving time by expressing this u of 0, u of pi over 2? This is very helpful when you're integrating weird radicals or weird exponentials. Saves you a lot of time. So, but again, here is where you may choose what's best for you. Do you want to change the limits of integration? That's fine. Do you want to ignore the limits for a while and then just do upper limit minus lower limit after doing a back substitution? That's fine for you. Just make sure to get the exact same result. You should get the same results anyway. All right, so let's go about the second integration. That is letter B. That is the integral of 3 sine t cosine squared t dt, also from 0 to pi over 2. How about another u sub? Okay, But in this case, let me write this in, let me use the commutative property of multiplication to see this use up a lot better. I'm going to write the cosine first, but I will also write this way, and that times sine t dt. This way, so we can u equals to this time cosine t du. Oh, careful with du. What's du this time? Negative sine. Negative sine t dt. That is sine t dt equals to negative du. All right? Let's change our limits again. I'm going to change them to the world of u. U of 0, u of 1. That is cosine 0, cosine pi over 2, cosine 0, which is 1, cosine of pi over 2, which is 0. Okay? And, well, let's do the substitution first. Okay, so this will be the 3 outside times the integral from 1 to 0. And don't freak out if you get the lower limit to be larger than the upper limit. We will fix this in a second. This is still correct. So, this is u squared times negative 1 times du. Where did I get the negative 1? This negative right here, all right? So, okay, let me take that negative outside. That is negative 3 integral of u squared du from 1 to 0. If you're still uncomfortable with the lower limit to be being larger than the upper limit, use the properties of integrals that you learn in Calculus 1. That is, that when you have the integral from a to b of some function f of x with respect x, that equals the integral of the same function f of x with respect x, you may reverse the limits to go from b to a, provided you simply change the sign. And actually, we can use that negative sign in front of this integral to reverse those limits. Okay? That's 3 times the integral from 0 to 1 u squared du, which is 3u cubed over 3, not plus c, from 0 to 1. Oh, that's going to give us the same u cubed from 0 to 1, and that's simply 1. In the same way we got it over here. All right? Well, let me do u 1 cubed minus 0 cubed. That equals to 1. Why not? So the result is a constant vector because the result of evaluating definite integral, it's a constant. So 2 constants or 3 constants, depending whether we're working with vectors in the plane or with vectors in space. All right, and to wrap up the section, actually, we're going to do another integration problem. Okay, but what is this about? So notice in this case we're given the derivative of some vector valued function. We're going to, which again represents the velocity, if you will. So we're going to go back and retrieve, so to speak, the position function. But they're also giving us an additional condition here, that is r of 0 equals to the vector 2, 2, 2, right? What is this? I mean, okay. So, what happens when you evaluate the integral of 2x dx? So, that's going to give us x squared plus some constant of integration. And again, this is where you put together the integrations with the solutions to a differential equation. That is because this c represents, when you have a function, whatever function f of x with a constant, with a c that we don't know what it is, that's basically representing a family of functions, you know? And well, so in some cases you may be interested in the member of the family that lives at a particular point. So you would do what it's called an initial value problem to find that value of c. All right? If you have taken differential equations, you have done this a lot. So solving a differential equation and get the general solution, and get the particular solution to find that value of c. I'm pretty sure for those of you who have taken it. Okay? If you haven't taken it, well, you still have seen this before in Calculus 1 to find the, what's it called, the constant of integration. Then you were given a condition, f of 0 equals to 3. So that means, this notation means you're looking for the member of the family of parabolas, in this case, that contains the point 0, 3. What do you do? Okay, so this is y equals to x squared plus c. So this will be, replace x with 0 and y with a 3. That means c equals to 3. So the function you're looking for is x squared f of x equals to x squared plus 3. All right? Now, we're going to repeat this problem, but in this case, depending on whether we're working on R2 or R3, in this case, for this exercise in R3, this initial condition will not be given as an order triple or order pair or in function notation. Well, so yes, technically it's a function notation, but as a vector notation, vector function notation. That means R of 0 equals the vector 2, 2, 2. So in this case, we're going to solve 3 of these problems in the same one. All right. So, the integration shouldn't represent the it shouldn't represent the challenging part. It's just what we're going to do next with the result. So we're going to go from r prime to r of t by integrating r prime of t dt. Okay, in this case, that's the integral of all this madness here. 4e to the t comma sine t. And by the way, I'm changing to component form. That's secant squared t dt. Notice in this case, this is not a definite integral. We're not given lower limit or upper limit. Okay. So let's evaluate this integral. I don't think for this one, I don't think we need to set the 3 integrals separately. But if they were more elaborate integrals, then that's my advice. Because we can integrate 4e to the t, which is simply r of t. So by the way, keep writing this r of t. I will show you why. The integral of 4e to the t, the integral of e to the t is itself e to the t times the 4. That's 4e to the t. The integral of sine, what's that? What's that? Negative sine. Careful. Negative sine. Oh, I'm missing something. Plus c1, comma. Negative cosine t plus c2. And the integral of secant squared, what's that? Tangent. Tangent t plus c3. So now, our job is to find out the values of C1, C2, and C3. Okay, so we're looking for a particular function, not just a function. We're not just getting a family of functions. We're looking for a family of functions. How do we do this? Well, using this initial condition. That means when we evaluate the vector valued function that we just obtained at 0, that should be equal to the vector 2, 2, and 2. All right, so R of 0, that means evaluate all instants of t at t equals to 0. That is 4e to the 0 plus c1 comma negative cosine 0 plus c2 plus tangent tangent 0 plus c3. Okay, evaluate all this. Well, e to the 0, that's 1. 1 times 4, that equals to 4 plus c1. Cosine of 0, that's negative. That's 1 times a negative. That's negative 1 plus c2. And lastly, tangent 0, which is 0, plus c3. It's just going to be c3. Okay, what are we going to set this equal to? Set it equal to the vector 2, 2, 2, because r of 0 is equal to the vector 2, 2, 2. Again, remember that silly property we talked about at the beginning of the semester when two vectors are equal if their components are equal? Well, here again, it makes more sense. We use that property to equate components. 2 equals to 4 plus c, 2 equals to 1 plus c squared, and 2 equals to c3. So that's going to give us a system of 3 equations, but actually every single equation will be one single variable. So 4 plus c1 equals to 2, negative 1 plus c2 equals to 2, and lastly c3 equals to 2. Okay, so this means c1 equals to 2 minus 4, that's negative 2. c2, okay, add 1 to both sides, that's c2 equals to 3, and c3 it's simply equal to 2. That's a given, right? So now we need to go back to r of t. R of t, that equals to the antiderivatives 4e to the t plus c1, which is rather minus 2, negative 2, and what else? What's next? Negative cosine t plus c2, which equals to 3, and c3, that is tangent t plus c3, which is simply 2. And in this case, no constants of integration. This is again a particular solution, if you will, a particular member of the family of vector valued functions, and we're looking for the particular member that contains the vector 2, 2, 2. All right? And I think this is a good place to finish this section.